In the last video, we discovered what artificial intelligence really is. But that leaves us with a much bigger question. How does a machine actually learn? Think about a child learning to recognize a dog. Nobody gives the child a mathematical definition of a dog. They simply see examples. Again, and again, and again. Eventually, they recognize a new dog they've never seen before. So can a machine do something similar? And if it can, what does learning actually mean inside a computer? Let's imagine we're trying to teach a machine to recognize dogs. We give it one image, then another, then another. Different breeds, different sizes, different backgrounds, different lighting. Eventually, the machine has seen thousands of examples. Then we give it something completely new, a picture it has never seen before. And we ask, is this a dog? The machine has to make a prediction. But how can it make that prediction without us giving it every possible rule? One option would be to write the rules ourselves. For legs, fur, 2 ears, a tail, certain shapes, certain patterns. But very quickly, we run into a problem. Not every dog looks the same, and some things that look like dogs aren't dogs. Some dogs don't even look like the typical image we have in our heads. The number of rules and exceptions would become enormous. So instead of trying to write every rule, what if we let the machine discover useful patterns itself? And this is the fundamental idea behind machine learning. Instead of telling the computer exactly what every rule should be, we provide examples. The machine analyzes those examples. It searches for patterns. And through training, it builds a model that captures useful relationships in the data. So the direction changes. Traditional programming says, here are the rules. Follow them. Machine learning says, here are the examples. Learn useful patterns from them. But there's an important distinction. Learning doesn't simply mean memorizing the examples. Imagine showing an AI 1,000 pictures of dogs. If it simply memorized those exact pictures, it wouldn't be very useful. The real goal is different. The model should learn patterns that allow it to recognize a dog it has never seen before. This ability is called generalization, and it's one of the most important ideas in machine learning. A good model isn't just remembering the past. It's using what it learned to handle something new. So, how does this learning actually happen? We start with data. The model receives an example. It makes a prediction. We compare that prediction with the expected result. If it's wrong, we calculate an error. That error provides feedback. The model adjusts its internal parameters. Then it tries again. Prediction, error, update, repeat. This entire process is called training. Here's something important. A machine doesn't become intelligent because it gets everything right on the first attempt. In fact, during training, it gets many things wrong. Imagine the model sees an image of a dog. It predicts, cat, wrong. The system measures the error. That error becomes feedback. The model uses that feedback to adjust its parameters. And then it tries again. So in machine learning, mistakes aren't necessarily failures. They can become part of the learning process. But when we say the model learns, what actually changes? Inside a machine learning model are many adjustable values called parameters. During training, these parameters are updated. You can think of them as tiny numerical settings that influence how the model responds to different inputs. At the beginning, those values may not produce useful predictions. Through training, they are gradually adjusted. The goal is to find values that allow the model to capture useful patterns. And modern models can contain enormous numbers of these parameters. One example isn't enough. 10 examples aren't enough. A machine learning model may need to process enormous numbers of examples. It makes a prediction, measures the error, adjusts its parameters, then tries again, and again, and again. Over time, the predictions can become more accurate. This is why training powerful AI models can require enormous amounts of data and computing power. Learning isn't one event. It's a repeated optimization process. But eventually we have to ask, when do we stop training? One way to think about this is through something called loss. Loss gives us a measure of how far the model's predictions are from the desired results. During training, we generally want that loss to decrease. High loss means the predictions are far from what we want. Lower loss means the model is performing better on the training objective. But there's a catch. Lower training loss doesn't automatically mean a better real-world model. Imagine a student memorizes every question in a textbook. They score perfectly on those exact questions, but then you give them a completely new question, and they have no idea how to solve it. That's not really understanding. Machine learning has a similar problem. A model can perform extremely well on the examples it was trained on, but struggle with new data. That's why we care about generalization. We don't just want a model that remembers the training examples. We want a model that learns patterns that transfer to new examples. This is why machine learning systems are evaluated on data they haven't learned from. We can think about the process in two stages. Training data is used to learn the model. Then new, unseen data is used to evaluate how well that model generalizes. If a model performs well on both, that's a much stronger sign that it has learned useful patterns. If it performs perfectly on training data but poorly on new data, we have a problem. The model may have learned the training examples too closely instead of learning patterns that generalize. Not every machine learning system learns in exactly the same way. There are three major approaches you should know. Supervised learning learns from labeled examples. For example, images labeled as cats or dogs. Unsupervised learning works with data where the correct answer isn't explicitly provided and looks for hidden patterns or structures. And reinforcement learning works differently again. An agent takes actions and receives rewards or penalties. Over time, it learns which actions tend to produce better outcomes. Three approaches, three different ways of learning from experience. You might think machine learning is something that only exists inside research laboratories, but you're probably using it every day. When a streaming service recommends a movie, machine learning may be involved. When your email detects spam, machine learning may be involved. When a bank detects unusual transactions, machine learning may be involved. When your phone recognizes your voice, machine learning may be involved. And when an online platform decides what content to show you next, machine learning can play a major role there too. It's already deeply embedded in modern technology. But machine learning has a serious weakness. A model can only learn from the information available to it. If the training data is poor, the model can learn poor patterns. If the data contains bias, the model can reproduce that bias. If the data is too limited, the model may struggle with new situations. And if a model becomes too focused on its training examples, it can overfit. So building a good machine learning system isn't simply about choosing a powerful algorithm. The data matters enormously. Let's put everything together. This is the mental model I want you to remember. We start with data. The model is trained on that data. Training adjusts the model's parameters. The trained model receives new data. It produces a prediction. That prediction can be evaluated, and feedback can be used to improve the system. So the cycle becomes data, training, model, new data, prediction, feedback, improvement. That's the basic learning loop behind machine learning. So now we can ask the question we started with. Did the machine really learn? If it simply memorized the training examples, probably not in the sense we actually care about. But if it can take patterns learned from past examples and use them successfully on new situations, then something much more useful has happened. The machine has learned a representation that can generalize. And that idea is at the heart of machine learning. But machine learning is only the beginning. What happens when we use neural networks with many layers? How can a machine learn increasingly complex representations? How do neural networks recognize images? How do they process language? And how did these networks eventually lead to today's generative AI? That's where we go next. Deep learning. In the next video, we'll uncover how neural networks learn, layer by layer. See you in the next episode.